All right. Hello, everyone. Welcome. James Dice, founder of Nexus Labs, where we strive to tell stories about smart buildings that might move the industry forward. How can we cut the adoption curve? How can we clarify the technology to help stakeholders make better decisions? And as part of that, we're proud to partner with Clockworks Analytics today to tell a slightly nerdy, very nerdy story about fault detection and diagnostic software that isn't very widely known in the industry today, with the hopes that it will help drive better software selection moving forward. So I have my guest today, Dennis Krieger. Welcome, Dennis. Can you introduce yourself and tell us what you do for Clockworks?
Yeah, absolutely. Dennis Krieger. I am the Director of Partner Success at Clockworks, which means I get to help engineering consultants and just HVAC services companies actually adopt software to go transform how they do services in buildings.
Awesome. So thanks for joining us today. One thing I want to talk about before we begin is that I feel like there's quite a bit of momentum happening right now in the analytics space. So just this week, the Smart Energy Analytics campaign just finished their report on their 4-year campaign, 6,500 buildings installed analytics. Quite amazing results that came through from that. And I feel like we're getting to this point where we're starting to maybe cross some sort of bridge to potential mass adoption. And with that, I feel like people are starting to get a better understanding of these tools and how they can be very powerful for building operating teams. So one of the pieces that when people start to use it more and start to understand this tool, one of the things that I hear a lot is that it's all about people and processes, to basically understand that when the analytics produces some sort of insight for a building operating team, the most important thing is that insight gets taken to action. So you get an alert. Now it's time to figure out, okay, how do we implement it? How do we verify that it was implemented and move on to the next one? Or else the point of analytics is what? It doesn't actually do anything. One of the things I wanted to do with this white paper, and we wanted to do with this white paper, is to say, okay, yes, the human is extremely valuable in the analytics process. No one's questioning that. But we want to point out that the human's role varies drastically based on the tool that the humans are using. And so how do you guys think about that at Clockworks?
Yeah, absolutely. I think even that LBNL study, what's amazing there is the measure of success is really in the completion of a task, a work order, an ECM project. And regardless of what your software is doing, that should be your measure of success, right? Not the number of faults you generated. It should be the number of tasks you complete. I think that's what everyone is really starting to appreciate now, that you can't just go throw in analytics software and expect your building to magically save 10%. It does require humans, and those humans should care about what their software is telling them. The tool still matters. And I think the nuance that we really hone in on within that white paper that we've been working on is that difference between an analytics output that is just essentially a sophisticated alarm, like here's a identification of a fault, versus the true fault detection and diagnostics, the ability to go deep into those issues, prioritize them, and act on them. And I think the ones that were successful in that LBNL study were the ones that were able to act on the information. I think that's the key difference between someone who achieves maybe 20% savings and someone who tries to set up their software for a long time and learns that it's a bit more complicated than you think when you get into the engineering analysis behind what's happening with those faults.
Yeah, so what we've been doing over the last couple weeks, actually several weeks, is really nerding out, getting into the details of what FDD means. So what we did in the white paper is we looked at, okay, what are all the ways in which people analyze data in buildings now? So you have building automation systems alarms, and then you have a lot of people, like we said, are now graduating to this concept of FDD software. But when you get down to it, there's actually two types of FDD software. There's one type that kind of stops at the first D, which is fault detection software. And what you have is a lot of people actually call it fault detection software. It's almost like as an industry, we've forgotten that second D is important. And so what we did in this white paper is went into detail about what that second D means, even getting to at the end, we actually specified, okay, here, if you want that second D, if you want true diagnostics, you have to have this checklist.
That's like a functional requirement or a spec for what the FDD should do and how it should operate. Again, with the objective that we want to drive more tasks, more activities in the buildings as a result of this information. And there are some just nuances and technical concepts that need to be incorporated into that software to really drive that type of action, a true proactive maintenance program within a building.
So we want to push people, if you want to go through that graduation of alarms to FDD, we have the showdown and the white paper that kind of explains the difference between the three levels. What we want to do today is go into some deeper concepts around what diagnostics mean, and Dennis has some slides to dive in for us.
Yeah, so let's bring those up. So we'll start with just some of the basic concepts, and I shouldn't probably say basic. These are incredibly nuanced and technical concepts that we're trying to present in the simplest way we possibly can. So we'll go through 5 key concepts, and then James, maybe we can bring it back to some examples in Clockworks to drive these points home. But let's start from the beginning. We have the same building blocks. Regardless of what software, what type of analytics you're doing in the building, we're all going to go into a building. We're going to try to find BMS controllers. We're going to try to find meters, and all those things present to us in really the simplest way possible: data points and devices. So on the left here, to start this conversation off, all analytics software will do some type of point tagging when they discover all these points in the building. And so whether you prescribe to Haystack or some other technique for tagging your data points, you're going to go from the kind of raw BACnet object name to some cleaned up point tag that you've applied. And I think the industry as a whole is getting really good at this left side. We're getting into now point prototypes with Haystack, this idea that the order of these text strings really matters, that you have a truly uniform tagged data set to start with. But what you often overlook is this idea that we need to go beyond simple point tagging. If you're tagging points without any objective behind it, there's really no purpose, right? Like, why am I tagging this point as a discharge fan state, for example? To get beyond that, we need to get into an actual data model or a data ontology. And this is, to me, one of the first and frankly one of the biggest differentiators between kind of a simple rules-based fault detection analytics platform and true fault detection in diagnostics. You need to give each of those points a meaning, and you need to map them to a data model that knows, hey, this point that I'm bringing onto this equipment is actually an air handling unit, and that discharge air temperature is going to be impacted by the reset strategy that it uses in the control sequence. This outside air damper is going to be impacted by the economizer type. And to understand those nuances, you have to go beyond what's in the actual BMS controller. You need to be bringing in variables from control sequences, equipment schedules, and even your own calculated points, things that don't exist in that controller, but you can produce using some engineering equations, if you will. So calculating airflows and the ideal damper position based on some of these known control sequences and equipment variables. So this is a hard line to me. I think there's a lot of fault detection software out there that can apply simple rules based on a clean tagged data set. But to really understand how your equipment is supposed to be operating, you have to get into this idea of a true data model.
Yeah, and in the white paper, we talk about how we use the economizer as an example. And isn't this a place where it really highlights the difference between the two?
Absolutely. Looking at this point list and trying to understand if your outside air damper is in an ideal state is really difficult, right? The BMS controller has a list of objects. I tried to reverse engineer this. I see there's a reverse air temperature. Maybe that's used in part of my economizer sequence, but to actually go through and apply that equipment type in your data model itself opens up more analytics capabilities. You can check for more things if you know the purpose behind this piece of equipment. And I think that equipment variable, that higher level kind of typing of the equipment itself and what it's supposed to be doing is critically important there.
And the way you just described that as another key point of the white paper is that maybe the central point of the white paper is that when you don't have the second D and parts of the second D, like this more advanced data model, then you need to make up for it with human intellectual labor to get the same results that you would with a tool that does a lot of that for you.
Absolutely. And I think there's quite a bit of that going on still in the industry. It's still amazing just thinking about the idea of having access to all this data in a clean tagged data set is incredibly powerful. But if you're still deploying your data scientists and senior engineers to go find these issues, then you really haven't unlocked the full capabilities of a fault detection and diagnostics software application. So moving on to point two, then this is where things get a little crazy, but it's important to understand this concept behind building custom rules and having a analysis engine that is pre-configured and ready for the points that you're feeding into it.
This is where we get into the more nerdy aspects of it. So
Yeah.
let's dive in, give it to us.
Far more PowerPoint art going on here to explain, but we'll ignore most of the complexity on this right side and just break down a simple concept here that a lot of fault detection software will build rules, and these rules live in isolation of one another, right? So you have a rule that's continuously monitoring your data and it's looking for conditions to be true. And this generates many faults that, again, are not really aware of one another. So going top to bottom here, you might identify that you have a hot water valve that's leaking and it shouldn't be doing that, and it's costing you money and energy waste. But you also might be detecting symptoms of that leaking hot water valve. And those rules don't know that they're not the root cause. So they're going to present just like the root cause of the issue does. So you might trigger a hot water valve leak by fault. You might also trigger a simultaneous heating and cooling fault. You might also trigger a high discharge air temperature fault. All three of these issues are related. It's one air handling unit, and these are all essentially symptoms of the single root cause that we've identified of the leaking hot water.
Such a powerful example.
It is. And I think the hardest concept to probably quantify in this example here is this concept of a false negative. And I think in our industry, this is one that we'll never really be able to speak to and measure, because just the nature of a false negative. If you haven't taken into account, for example, that economizer sequence, and you're not checking the ideal outside air damper position to optimize the energy performance of this unit, you may miss things like, hey, this damper position is not where it should be. We could be taking advantage of free cooling on top of all the issues we're having with this hot water valve leak by. So the false negative concept and the idea of triggering many faults off of symptoms leads to this kind of noisy list of faults, and still this feeling that, like, I need to go in and investigate more. I need to look for more things because I don't know if I have a rule set up to catch X, whatever I'm trying to investigate. So
this is where you need your analytics super user, is what a lot of people call them, to then go in and pull some trends up and sort through all of this out manually with some charts, essentially.
Absolutely. And still, what an amazing tool to have, right? To give someone that capability. But at a minimum, you need to factor that additional step in when you're evaluating these different applications, and understanding that, like, building rules in a custom way is a lot different than having an analysis engine that is pre-configured.
And this is another place where when you're depending on that intellectual labor, you're limiting your scalability when you're doing something that the software could be doing for you. And I've always had this feeling as an end user myself, is that I'm thinking about this in a way that could be algorithmic. I'm actually doing something that the computer can do. So how does Clockworks do it behind the scenes in a way that is scalable?
Yeah, so the first thing to know with Clockworks is that there is truly one comprehensive analysis engine, meaning we have 2,400 buildings on the platform today. We have 400 million square feet of space across those buildings. Every single data point that we've collected is fed through the same analysis daily. And that analysis engine is not a kind of siloed rule set. It is a connected set of algorithms. What that means is when we look at an air handling unit, we're going to account for the fact that that preheat coil is contributing heat to an airstream that is being cooled by the cooling coil. And when we check those things, we do it holistically. So you can output two root causes instead of many symptoms, because that analysis is truly connected. This is one of those nerdy behind the scenes concepts that we're trying to speak to more, because it's an important one if you want to have a truly actionable list of issues in your building, right? You don't want to add that additional step of, oh, I got to sort through this, filter it, and do that second level of investigation to figure out which one is truly worth my time.
Yep. And these graphics are in the white paper, and people that want to go through this whole if this, then that analysis can dive in there.
Absolutely. And to your point earlier, James, you're building all of your engineering analysis into each of these rules. And you know that's giving you the tool to do that is very powerful, but you want to scale. You want to be able to take your James economizer rule that you just built and spend all that time on and deploy it across every building that you're trying to manage or optimize. And every fault detection and diagnostic software platform out there wants to be scalable, needs to be scalable. One of the challenges with the custom rule approach is that they rely on matching point types, right? So if I've built a rule to detect a leaking hot water coil valve and it uses the preheat discharge temp, mixed air temp, fan status, hot water valve, I'm looking to match those conditions across every piece of equipment where I might want to detect the same thing. This instantly breaks down when you've seen more than one controller, right? Like we all know that there's a lot of diversity in the type of backnet objects you get from an AHU controller. And inevitably, your rule set has to customize for each of those diverse applications. So if you don't have an intercoil temp, how are you going to detect the same thing? If this unit doesn't have a fan status, how are you going to know when it's on? These are very seemingly simple challenges, but it requires a lot of sophistication in how you route the analysis and map it against these diverse controller types. And a simple rule simply can't do that. It's hard to match these one-to-one. So we look for this different approach of guiding each type of equipment, each controller configuration through a set of logical paths to say, hey, what tells me when this thing is on? What points are available to determine airflows, delta T's, statuses, and how can we get to the same output, the same, hey, this hot water coil valve is leaking, regardless of if we had 10 points on that air handling unit, 24 points, whatever it might be. We want to give you the highest quality output with the minimum amount of data inputs that we can see, right, on each controller.
Yeah, I like to call this best available information. Like we're going to use whatever we have in order to get the job done, but sometimes we might not have the best available, so we'll take what we can get, essentially.
Absolutely.
Just so people are clear. So the air handler 3 there that doesn't have a fan status, what you're basically saying is that since it does have a static pressure sensor, we're able to use that as a proxy to say, hey, the air handler's on, and that be the rule. Okay.
Yeah, and the most frustrating thing for anyone who's been doing analytics is when you've set up that nice rule, you've spent a lot of time putting your engineering analysis into a rule set, to see it not connect, not deploy on that next piece of equipment is extremely frustrating. So to have these automated paths where we can guide you to the same analysis in many different ways allows you to be scalable. It's simply impossible to customize each rule to every piece of equipment. You should be bringing your equipment into one cohesive model that it has the intelligence baked in to guide it to the right place.
Got it.
I think maybe the last point here is just if you're stopping with the engineering check, like the airflow is off, the set point isn't where it should be, you're really selling yourself short. Because I think in the world we live in, we all need to also associate these issues to their dollars and their energy waste or their impacts to indoor air quality, whatever that might be. This is also incredibly hard in the kind of siloed rule approach where a fault lives in isolation. So if I'm checking for leak by on a hot water valve, but I'm also checking for simultaneous heating and cooling, which one am I going to do my energy calc on? Because they're both essentially detecting the same issue, right? So if you apply your simple rule of thumb engineering calc to this and come out with an energy waste, you're likely going to be double counting or even triple counting some of these issues, depending on how many rules you've established on this particular piece of equipment, right? There's a quantum leap forward when we get into this idea of truly automated regression modeling off of these issues. That air handling unit has one airstream. It has one preheat coil, one cooling coil, and maybe a reheat coil, right? So we're adding heat, we're cooling, and we have one airflow to measure. There should be one analysis. You should not be duplicating how you're analyzing that piece of equipment. It requires a holistic view to be accurate. So within Clockworks, we've automated this step of the process, and it goes beyond the simple statistics and also gets into the idea that you need to understand the sequences behind these systems. When does my heating system enable? what does that mean to my leak by savings? Like I can't count leak by cost savings during times when my boiler plant is not on, right? Simple things like that are incredibly difficult to do when you're building them into each rule. It's much easier to do in a holistic set of algorithms that are accounting for the building profile as well as those unique conditions that you've detected in the equipment itself.
And what are you trying to say by observed week versus model? Because I feel like this is a really important concept as well.
Absolutely. There's this kind of annoying situation where we all want to be very proactive, which is great, but we also need data to extrapolate some of these impacts to their full, say, year, for example. And so you need to be able to observe a period of time that is representative of your conditions. Hey, we detected a leaking hot water valve during an outside air temperature range of 50 to 60 degrees, let's say. We then need to apply that regression analysis to model the projected savings for the rest of the year. This is an incredibly advanced, essentially like an M&B technique. A lot of us who've been in analytics have done this manually in Excel spreadsheets. James, you and I, we've done the hobo data logger thing where you connect and try to do this observed or measured week as well.
Yep.
Why not automate that? It's all the same analysis. We know the statistics on how to validate these models. If your fault detection and diagnostic software is not taking this next step, then you will be doing this if you want to put dollars next to everything that you're fixing the building. And frankly, no one wants to do that. At least no one I've met wants to do that, myself included. So it's nice to automate that final step and make it as accurate as possible.
That's what I always say as energy engineers want energy savings. If you want to automate what it takes to get to those savings, I think they'll be okay with that because they can be their intellectual capacity can be used to solve the problem rather than get to what the problem is to begin with.
Absolutely. Yeah. I don't think any of us are missing that 8760 TMY3 calc we had to do in Excel for every single measure, right? And then last but not least here, like all this has real financial implications on what software you're investing in. And this might be to someone who's actually comparing Apple's different software to go optimize their buildings. This might be the most important point. Your software and the savings that you are going to achieve because of the deployment of that software are going to be impacted by the human element here. The additional time spent configuring rules, investigating and finding root cause, doing that spreadsheet calc for the energy savings. If you're spending time doing that, you're increasing the cost of your program, right? And these two charts here, left and right, just a simple financial breakdown, the software costs being the blue chart here, the blue bars, if that's the same, completely apples to apples, if you're spending too much time doing those additional steps, you're gonna increase your costs. You're also going to decrease your savings. This to me is one of the biggest outcomes of that LB&L study that just got updated. There's a lagging time between when you deploy software and when you achieve the full potential of savings in your building. And that time is really in the logistics of completing projects, right? And the takeaway here is the more time you spend tweaking your software instead of fixing things in your building, the worse your return on that investment is going to be. And that's simple math, right? This is actually the exact profile from the original LB&L study, which I should update. Now they have the latest results out.
There you go.
So those are the big concepts. James, like you said, there's a full paper where we broke down some of this in more detail, but from a high level, this is the message we're trying to get out there. It's that you should really pay attention to the nuances in the software. And to a point you made earlier, James, like there is momentum building in analytics software in general. And I think from my perspective, someone who demos and tries to sell software almost every day, people are now asking these questions. It's really interesting to see. 5 years ago, I was explaining the basic concepts of connecting buildings to the internet, getting data to the cloud. Now we're talking more and more about these nuances of root cause identification and automatic costing using advanced energy modeling techniques. More and more people are wanting this baked into their software and asking the right questions to really evaluate this stuff.
So do you want to go ahead and show us what it looks like in the platform?
Yeah, let's give a quick little test drive here in the real world. So for those who haven't seen Clockworks analytics before, our goal is to everything we just talked about in the most automated way possible so that all you have to do is go act on this information. We're trying to eliminate as many steps as possible so that the people who are operating or servicing buildings can do what they do best. Go fix the actual mechanical failure, improve the indoor air quality, whatever their objective is. So this list is the output of our fault detection and diagnostics analysis that we run. And by default, we try to give you basically the most intelligent punch list of activities you can go perform in your buildings to realize cost savings, to improve the energy performance of your building, to improve the indoor air quality of your building, nowadays more and more important, and to also improve the equipment reliability, looking for things like cycling compressors and damaging conditions for your equipment. How you attack this list is really based on how you work. And this is a tie back to that kind of human in the loop concept, James, where not everyone logs into Clockworks every day. And I think some people would, try to emphasize how fast they're running their analysis or how many faults they're detecting. But in reality, the people who run these buildings don't need more things to look at every single day. They need a prioritized list that they can bring into a proactive maintenance program or incorporate into, say, a quarterly service to a building. So this list by default gives you that daily punch list. Here's your top priority of issues, and whether I am tackling energy and ranking this by the cost savings associated with that day's issues, or whether I'm ranking this list by their impacts to indoor air quality, that's based on what I'm trying to solve for in the building. The list dynamically updates based on what you're trying to do.
One of the things we laid out in the white paper is that prioritization is one of the things on the checklist that you need to look for to know whether you're getting diagnostics or not. And it's being done in different ways. And so we break that down in the white paper.
Absolutely. And again, those priorities change based on the type of service you're doing. So this daily list of issues might be appropriate for someone who's fully embraced this proactive maintenance routine within their building. Maybe I'm an owner operator who is doing this every day. But this idea that you might also be looking at this more from even a monthly list. So maybe I'm an HVAC services company and I know I'm going to go to a facility next week. What were the last month's highest priority issues? So I regenerated this entire list. Now we're looking at a month of data and you can see these costs are climbing up. So in the last month, you wasted $20,000 on a single item here with many issues. This sentence here that you see is essentially many faults being grouped together into one single analysis, which we'll drill into here a bit more. So James, I think the other kind of key concepts we pointed out is that, again, fault detection stops at that list we just saw. Here's a bunch of issues you need to go figure out. Diagnostics does that step for you. How do we show you that we've investigated all these things, give you all the information you need to actually act on the information, right? So within a single diagnostic within Clockworks, we give you all of that in one place. So this single analysis of AHU3 is actually running across all of the points in this list. So there is no kind of single fault here. It's many dozens of points feeding into one comprehensive analysis of the air handling unit. Because we're doing this all holistically, we can generate these simple statements that tell you problems and possible causes. So my problem of simultaneous heating and cooling is where we're wasting a lot of money. So in the last month, we've wasted $20,000 on this one issue. The possible cause that we list first here is that you have a leaking preheating coil valve. All the text that you read here is actually an output of our analysis, meaning these numbers are dynamically generated. The possible causes are ranked in order of likelihood based on what we're detecting in each of these. We also are going to detect things that aren't necessarily related to that issue, but could be an opportunity to investigate while you're fixing that issue on the air handling unit. So if I'm going to go fix that valve, I might also want to know that my supply temperature set point is not currently resetting. Is this impacting comfort? Not at all, but it is wasting energy. And while you're there, you should investigate the control sequence. See if there's an override in place that you can remove. And all this gets bundled into an annual projection of savings. And for anyone who's a statistics nerd, there's quite a bit going on here. So we take all that data that we analyzed, we project it out, again, using regression modeling techniques. And you can get into all the statistics if you want to, or if you're like me, you can just take that big number and know that everything else was checked for you automatically. Even conservative adjustments to make sure that we're comparing a like-to-like data set. So we're saying that in the projected year, you could save over $200,000 if you fix this issue we're also telling you that based on the model that we validated, that only represents 74% of the full year because of the kind of verification or validation of the model that we're doing to ensure we're never giving you an aggressive number that you can't defend.
Awesome.
The rest of the stuff's kind of just, I don't know, the icing on the cake. We're going to generate trends for you. So 5-minute interval data showing you temperatures, showing you when these issues occurred throughout the month period that we're analyzing, showing you that supply temperature reset. So here's why we recommended you implement that reset strategy, because right now your set point is locked in at 54 degrees. And we're even going to get into this concept of comparing ideal versus actual conditions. And to me, this is the final kind of emphasis against that data model concept. If you can't produce ideal conditions on a piece of equipment to compare your engineering checks against, then you're not really analyzing that equipment. You're just looking for faults. So in this case, we're modeling an ideal heating rate of 0. That's pretty easy, right? The valve should be closed. You really shouldn't be heating at any time because you have leak by, because we can detect a delta T across this coil, and because we know the airflow on the unit, we can actually calculate the energy that you're adding into this airstream from that leaking valve, that leaking preheat valve. And because you've heated up that air, guess what your cooling coil is doing? It's making up for it. So we're also calculating the ideal cooling rate if that heating weren't occurring in the actual, because you're leaking by. This level of modeling is what I'm talking about when I say you need a data model that understands how this air handling unit works and understands that something as simple as a preheat coil is upstream of your cooling coil. That matters because that means I can automate this calculation and know the impacts between something as simple as a leaking coil, right?
Yeah, one thing I like about this, as you scroll down, you started with the main insight, the main root cause, the main action that needs to happen. Whereas when we talked about, when we were going through the slides, our past lives, if you will, we would start out with this much longer list of faults. You talked about all the symptoms versus root causes. You'd have all those thrown into one list, and you would have to go through charts like this to then investigate each one to get to that root cause. But one thing that we talked about in the white paper too is that when you start with root cause, it's not that these charts aren't useful, but these charts are more just giving you backup information for what that root cause is, sort of explaining to the human how the computer got to the conclusion versus supporting the human and manually getting to the conclusion on our own.
I think it's like playing to just trusting the output, right? Giving the user confidence that, yep, we checked that, right? Like I think when all of us engineers, we need to see it. We need to see it to believe it. I would never trust a text output saying, go fix this valve, we think it's leaking. I would instantly say, show me the data. To have this kind of automated output that goes beyond just like simple trends and into modeling ideal versus actual conditions, it just gives you that sense that, yep, I'm ready to go hit that button, create a task, and turn this into a work order. I don't need to spend another second looking at this. I've got all the information I need. And I think that's how we get to that final conclusion that says the difference between FD, fault detection, and FD plus the diagnostic side is really that. It's just, I trust this enough to go act on it. I trust it enough to take those cost savings and put them up somewhere in a report to say, this is how I've impacted the building. And I think that's what every team needs to really turn this into something that becomes a proactive maintenance program or a digital service, right? Like they need all that content to be reportable, to be instantly actionable. And these little technical nuances are the difference, right? Between successful programs that on that LB&L study get you to 20% plus savings and the ones that kind of dwindle out. They hum along, get a few percent here, and then you see that no one's really adopted it. No one's really embraced it as something they're using to shift to that proactive maintenance operation, whatever that might be.
And that trust is a good way for us to close down this video. So we would love for you to go check out the white paper. We'll put a link in the description of this video and let us know what you think. Thank you.
Thanks.